take a look at today's lesson. Today we will identify the vertical and horizontal asymptotes of rational functions, and we will be able to explain how to find the vertical and horizontal asymptotes of rational functions. So let's take a look at today's lesson. Let's take a look at today's do now. We have given the function f of x is equal to x squared plus 3x plus 1 all over 4x squared minus 9. We want to determine the domain of the given function using set notation. So how do we find the domain of this function? Pause this video, try this question out. Alright, so for this part here, to find the domain, we set the denominator not equal to 0. Our denominator is 4x squared minus 9. I set that not equal to 0. I factored this difference of perfect squares, and I got x cannot equal negative 3 halves and x cannot equal positive 3 halves. So the domain written using set notation, that would be x such that x cannot equal those values. Part B wants us to use our calculator to sketch the graph of f of x. So all we're going to do is input this f of x into our function and just look at how the function is shaped. So on your graph, you should see something that looks like this. So it's not going to be as accurate because we're sketching this, but there's going to be one important thing. Right here, where the functions are going down and up, right, going in opposite directions, this value here has to be one of our walls or one of the things we do not want. Over here, the same thing. This must be the other piece of our domain. So I'm going to just label that piece. Using this graph, I'm going to be able to determine the domain using limit notation. So we are going to start with that x is equal to or heading towards negative 3 halves from the left of our function. So from the left of our function, as we get closer to this negative 3 halves, we go down. I'm going to do it again to the same x value, but this time heading towards the right side. So if we look at this, our function is going upwards, which means it's going to positive infinity. We're going to do this 2 more times. What happens to your function as you head to positive 3 halves from the left? So from the left, we are going down to negative infinity. And last time, the limit as x approaches that same x value of positive 3 halves from the right side, we are heading up to positive infinity. We have what are asymptotes and how do we find them in rational functions. So a rational function, again, is a function that looks like a fraction and has a variable in the denominator. We will need to know and find the key features of rational functions. So what are our key features? The x and the y-intercept, and also the domain. So we find the domain by setting the denominator not equal to 0, solving and excluding those values or value from the domain. To find the x-intercept, we know the x-intercept is a point on the x-axis, which means we're always going to have some number comma 0, letting us set 0 for our y and solving for x. To find the y-intercept, we know that that is a point on the y-axis, which means that we're always going to have a 0 comma a number, in which lets us input 0 for x and solve for y. And then we have asymptotes. So asymptotes are walls. An asymptote is a line that continually approaches a given curve but does not meet it at any finite distance. How do we find asymptotes of rational functions? There's two types of asymptotes. Vertical asymptotes, which are an invisible vertical line in which the function approaches but never ever reaches. So it will never cross these vertical asymptotes. The steps that you take: you factor the function, both numerator and denominator, if possible, cancel out like terms, set the denominator equal to 0, write your answer as an equation. The second type of asymptote we could deal with is a horizontal asymptote, in which we have an invisible horizontal line in which the function approaches, but in this case, some functions will sometimes cross it. So different functions will do different things. The vertical asymptotes functions will never cross, but the horizontal asymptotes, sometimes you will cross over or hover around it. There's three types of cases with horizontal asymptotes. If the top degree is less than the bottom degree, then we set our equation to y equals 0. If the top degree is greater than the bottom degree, then there is no horizontal asymptote. If the top degree is equal to the bottom degree, then we divide leading terms, coefficients, and simplify. So that's a lot to remember. There is an acronym to help you remember all of these. So we have Bob Yo, we have Bot No, and we have Eats DC. What do these things mean? Bob Yo. Bob means big on bottom. If you have a big on bottom, we yo. Yo means y equals 0. That's the equation of our horizontal asymptote. So what's an example of something that looks like this? You could have your function equal x squared minus 4 for the numerator and x to the third plus 2 for your denominator. What you are looking at is the degree. Where is the exponent larger? It's larger on the bottom. So that means the horizontal asymptote is going to be y equals 0. Bot no. Bot no stands for big on top. If you have big on top case, that means we have no horizontal asymptote. So how would that look like? That would look like literally the same exact thing as before, but reverse. Let's say x to the third plus 2 over x to the second minus 4. Where is my exponent larger this time? Larger on top, which means there is no HA. The last case, Eats DC. Eats DC stands for exponents are the same. If you have exponents are the same, what do? You DC. What does that mean? You divide coefficients. So a case like this, we would have our function as f of x is equal to 3x squared minus 5 over 2x squared plus 1. Here, if we look at our exponents, they're the same. Exponents are the same. What does that tell us to do? To look at the leading coefficients, and we are going to divide them. Divide and simplify. So in this case, my function or my horizontal asymptote would be the line y equals 3 over 2. That's its simplest form. Okay, so let's try this out. We have given our function f of x, which is equal to x minus 1 over x squared plus 5x plus 6. What we are going to do is we want to algebraically find all these things. But before we do anything, we're going to start off by looking at f of x function and factoring everything we can. And the only thing we can factor is the denominator. So here is my factor form of f of x. Now what we are going to start off doing is determining if we need to sometimes use this factored form function, or if using the original function is more quicker to work with. So for the vertical asymptote, to find the vertical asymptote, we have to set the denominator equal to 0. So in this case, what I'm going to do is I'm going to look at the factor form, because I'm going to set my x plus 3 factor times x plus 2 factor equal to 0, giving me my answer a lot quicker than me having to factor it. So I have two vertical asymptotes. X is equal to -3 and x is equal to -2. Next one we want to find is the horizontal asymptote. So to find the horizontal asymptote, what we need to remember is that Bob-Yo case, that Botno case, or that eats DC. And what we're going to look at is the original function's leading exponents. So we have x to the first and we have x to the second. This exponent is larger in the bottom, so we have big on bottom. That's our Bob. When we have Bob, our HA is yo. What does yo mean? Our horizontal asymptote is the line y equals 0. C wants us to find the x and the y-intercept. So what we're going to do for the x-intercept is set y equal to 0. So here I'm going to replace our f of x with 0, and I'm going to use the original function. So if I cross multiply, I will get 0 equals x minus 1, which will give us our x-intercept of x is equal to 1. The y-intercept. We find the y-intercept by having 0 be replaced for x's. So we're going to look at, again, I'm going to look at the original function, plug in 0 for x's, and solve for our y. And we get the y-intercept to be -1/6, or as a point 0, comma, -1/6. Part D wants us to label all key features on the graph. So we have all the key features here. Let's start by labeling the vertical asymptotes. So we had two vertical asymptotes, one of which is somewhere here. I'm going to put dashed line, arrows at the end, and I'm going to label this x value as -3. My other asymptote is somewhere here at -2. So there are my vertical asymptotes. I am going to label my horizontal asymptote. Horizontal asymptote is the line y equals 0, which means it's the x-axis. And again, dashed line, and I'm going to label it. Besides this, we are going to need to label that x-intercept and the y-intercept. So the x-intercept is the point 1, 0, probably right here, 1, 0, and the y-intercept, super close, is somewhere here. The y-intercept, let us label it 0, -1/6. It's very close to that 0, so it kind of looks like it is 0. And that's all the labeling that we have. Part E wants us to determine the domain of this function using limit notation. So to do that, what we're going to identify are our vertical asymptotes. And we're going to be heading towards those vertical asymptotes. So to not scroll, I'm going to just keep it here. The limit, or let's start with the domain. The domain would be the limit as x approaches that first asymptote of -3 from the left. From the left, where do we go? We go down to -infinity. What happens as I approach that same vertical asymptote, but this time from the right side? We go to +infinity. We're going to look at our second asymptote, which was -2. So we're going to say the limit as x approaches -2 from the left, and then again from the right. So from the left, we go up to +infinity. From the right, we go down to -infinity. And that is our domain. The last thing that we want to do is we want to determine the end behavior of this function, and we want to again use limit notation. So the end behavior of rational functions are awesome because they are always going to be equal to that 0. So the ends is what's happening at the very ends of our function. So for part F, the end behavior. We're going to look at the limit as we approach -infinity. Where do we head? And then the limit as we approach +infinity. Again, where are we heading? So the end behavior always is going to equal whatever your HA was. In this case, our HA was y equals 0, which means that the very ends of our functions are heading to 0. And if I look at my graph, that looks like exactly what's happening. It's getting closer from the very ends and closer to that 0. And that's all about rational functions, asymptotes, intercepts, and domain.